Welcome back, everyone. In this video, we're going to be talking about something called standardized distributions. We have been talking about finding single z-scores within a distribution, identifying a single score. But when we standardize a whole distribution, we're basically relabeling all of the scores within the distribution. So let's take a closer look. When we standardize the entire distribution, we take every x value that is possible and we transform it into a z-score. And when we do this distribution has three different properties. It has a certain shape, it has a certain mean, and it has a certain standard deviation. So let's talk about each of these. First of all, the shape of the z distribution is going to be exactly the same as the original distribution. Basically, we're just relabeling the x-axis. So the shape is going to stay the same. The values aren't going to change, but the labels will change. So each individual score stays in its same position within the distribution and the shape remains the same. So here's an example right here. We have two different ways of labeling a distribution. The very top part, as you'll see, I've circled an X because these are the scores. So we have one person had a score of 0 and two people had a score of 2. One person had a score of 3 and so on. And these are the actual scores. If you look down at the next distribution, it's the same set of scores, but relabeled in terms of their standard deviation. So as we look at the top distribution here, we have the standard deviation here, and it goes from 3 to 5, so the standard deviation is 2. So right now, at the bottom where we have all the scores turned into z-scores, we now have a z-score of 1, which is equal to 1 standard deviation. What is 1 standard deviation in this case? It's 2. So 1 standard deviation is 2, and it's still 2 scores here, but we have it as a z-score of 1. So z-score is equal to the standard deviation. But z-scores are always listed as 0.5 and 1 and 1.5, etc. And the interval between 0 and 1 on a z-score is the standard deviation width. So percolate on this a little bit, really look at this to see exactly what it means. We're basically just relabeling it by, instead of saying what the scores are, how far away they are from the mean in terms of standard deviation. So the z-score distribution, you probably want to write this down, will always have a mean of 0. So we just kind of recalibrate everything and we put the mean as 0. So it makes it very easy to identify locations. All positive values are above the mean and all negative values are below the mean. And so we'll take a look here. At the top we had a mean of 3 when we're just talking about our scores. But when we put them down in a standardized distribution, the mean becomes 0. So that's sort of dead center 0 is where the mean is. And then we have standard deviations above the mean and standard deviations below the mean. So the mean will always be 0 in a standardized distribution. And finally, the z-score distribution will always have a standard deviation of 1. So z-score values are the same as the number of standard deviations from the mean. So a z-score can be interpreted as this is how many standard deviations the score is from the mean. So we'll take a look again here. Here are the scores. And in this case, we have a standard deviation. We know a standard deviation is 2. So 1 standard deviation above is 5. 1 standard deviation below would be 1. But as we look down here, what we do is we just turn that width of 2 for the standard deviation, we call it 1 in terms of the z-score. So this standard deviation of 2 here equals a standard deviation of 1. It's one of these standard deviations. So as you look at this distribution, we have a mean of 100. What is the standard deviation? Well, if you're looking at the scores, the standard deviation looks like it's 10. So we draw a little line over here to the first designation, and that's 110. So 1 standard deviation above this mean is 110. What would 1 standard deviation below the mean be? It would be 90. But if we're putting this on a standardized distribution, this mean of 100 becomes 0. And what would have been the standard deviation of 10 becomes a z-score of 1. This z-score of 1 equals the standard deviation of 10. Z-score of 2 would be 2 standard deviations. 10 plus 10 is 20. But we don't think of it that way when we standardize the distribution. We say it's 2 standard deviations away from the mean. 1 standard deviation below the mean. How many points less is that? It's 10 points less because that's the size of 1 standard deviation. All right, lots to think about. So we're going to do some learning checks now, and actually these are tricky, but that's okay. Hang in there. And this might be a part of the video that you're going to rewind and watch again a couple different times. So let's say we have a distribution with 55 and a standard deviation of 6. And we want to standardize it. Now this is something we do sometimes, is we standardize it to have set values. Maybe not a value of 0 for the mean. Sometimes we can just pick a number and say this is what I want to standardize it to, with a standard deviation of 10. So we're going to standardize the new distribution, and we're going to find the value for a score of x equals 52 from the original distribution in the new distribution. All right, let's take a look. So here we have the information for the old and the new. The old distribution had a mean of 55, standard deviation of 6, and the score we had in the old distribution was 52. The new standardized distribution has a mean of 50 and a standard deviation of 10. So we need to figure out what would the score of 52 be if it was put on this new scale. The first thing we have to do is find the z-score for 52. We need to find out, in a normal distribution, where would this score be in a standardized distribution. So what I'm going to do is I'm going to use our z-score formula. Z equals the score, which is 52, minus the mean of 55, divided by the standard deviation. 52 minus 55 is a minus 3, and 6 is the standard deviation. So we have a negative 0.50. That is the z-score for 52 in this distribution. The z is equal to negative 0.50. Now that we know that the z-score for a score of 52 is negative 0.50, we just ask ourselves, well, if the distribution had a mean of 50 and standard deviation of 10, what would be the score at a negative 0.50? So in this case, the score is unknown, and we're going to use that fancy formula I showed you previously, where we're going to take the z-score of negative 0.50, we're going to multiply it by the new standard deviation of 10, and we're going to add the new mean of 50, and so we'll do this formula. Negative 0.5 times 10 gives us negative 5, plus 50 gives us a score of 45. So that means that a score of 52 in this distribution would be equal to a score of 45 in this distribution, because a score of 45 is a half a standard deviation below the mean. Standard deviation is 10, so half of that is 5. A half below would give us 45, right? So let's just double check this. The mean is 55. It's a half a standard deviation below. The standard deviation was 6. Half of that is 3. 55 minus 3 is 52. That's how we can kind of check our work. Let's try another one. Here's the next one we're going to try. We have a new distribution with a mean of 15 and a standard deviation of 8. And we're going to standardize this old distribution to be like the last one, with a mean of 50 and a standard deviation of 10. When the new distribution is standardized, what is the value for a score of 17 from the original distribution? So as I look at the score 17 compared to the mean of 15, I know it's above the mean, so it's going to be a positive z-score I'm going to be looking for. Let's dive in and give it a try. So once again, our old distribution has a mean of 15, a standard deviation of 8, and we had a score in there of 17. So the very first thing I need to do before I figure out what a score of 17 would be in this distribution is I need to figure out the z-score for 17. What is the z-score in this distribution? Where is it located? So I'm going to take my z-score formula, which is my score of 17 minus the mean divided by the standard deviation. So 17 minus 15 is 2 divided by 8, and that gives me a positive 0.25. So that is the z-score for this score in its original distribution. If I draw out a normal curve, it's going to be somewhere around here. It's a little bit above the mean at a positive 0.25. I want to make sure that this score keeps its shape but has a different distribution. So the next thing I need to do is find out what would this score be with these parameters. So let's take a look. We're going to use the same formula we used before, where x is equal to the standard deviation, or the z-score, let's start with that, a positive 0.25 times the new standard deviation of 10 plus 50. And then we have 0.25 times 10 is 2.5 plus 50. And that gives us a new score of 52.50. So this is the same as the score of 17 would be in this distribution, with this mean and this standard deviation. So let's think this through just a little bit. The standard deviation here is 8. There's a difference of 2 between the score and the mean. 2 is a quarter of 8, basically, so it's a quarter of a standard deviation above. So I could just do this without even doing any math. I could say, well, what's a quarter of 10? That's 2.5. 2.5 plus 50 is 52.50. All right, I'm going to stop here. And in the last video, we're going to do some more practice and talk a little bit more about the logic of using z-scores.